One idea that really helped us to see this and visualize this was the idea of streamline geometry. And if you remember, we discussed also two other representations of geometry of a flow field, which were called a strict line and path line. If the flow field is a steady state, if you remember, we showed that these three concepts, a streamline, a strict line, and path line, are all equivalent to each other. And in that case, in the steady state case, you can easily gain a lot of knowledge about the flow field just looking at the shape of the streamlines and how they are changing in a space. So imagine two streamlines for a given flow field look like that. By definition, a streamline is always parallel to the velocity vector. So at each given point, I can easily see that the velocity vector is parallel to the round streamline. One important thing that you can clearly conclude from that is the fact that there is no way fluid elements can cross a streamline. Because their velocity is always parallel to the streamline, there is no normal component to make them cross the streamline. Now if I take a fluid element that initially was between these two streamlines for a 2D flow, and I follow its trajectory along this streamline, I can see that in the next moment it may get into a new position, such as this, and in the next moment it's going to go to a new position, such as this. The basic idea that flow cannot cross the streamline boundary tells us that as fluid elements go through this contracting or converging pair of streamlines, the flow rate must remain conserved. If the flow rate or volumetric flow rate is the same between here and here, the fact that the cross-sectional area has narrowed down just visually tells us that probably here we have a low velocity for the fluid element, whereas here we probably have an increase in the velocity. So that's why it's useful sometimes to just draw and plot streamlines. The visual sense that they give to you can be kind of qualitatively or sometimes even quantitatively connected to things such as velocity and acceleration. This flow definitely will give acceleration to fluid elements. It's a steady, which means that if I look at the same point at different times, they all have the same velocity, but for a given element, as I move with it, I go from a region of lower velocity to a region of higher velocity. This advection in a velocity field that gives me a change in velocity will give me non-zero advective terms that will translate into fluid acceleration. These are important sources of acceleration that we need to be careful about. Now, the other aspect that is important in this flow field, as you can see, is not only about the translation of fluid elements from one region to the other region. The other aspect is about the shape of fluid elements and how they are deforming and changing as they are moving. We start with a almost rectangular fluid element. It becomes a little bit squished, and it becomes more and more elongated as it goes through the flow. And that was the point that we discussed, the fact that in fluid motion, it's very important not only think about motion of fluid elements, but also the deformations in the shape that are at the same time happening. Remember, we are not dealing with rigid particles. Fluid elements are deformable. They can get twisted. Their shape can change as they deform. And that was the main idea behind the section that we had called as kinematics and deformations. And again, to remind you what was the main principle there, we took a rectangular or square shape fluid element. We labeled it as A, B, C, D. And we discussed what's going to happen when it goes in the next instant of time to a new position and a new shape, which we describe as A prime, P prime, B prime, C prime, and D prime. We can see that two things can happen at the same time. You can have a change in respective length of different sides of this square or rectangle. For example, BC can become shorter or larger to B prime, C prime. The other change that can happen is the change in the angle. For example, here I started with 90 angle between these two, but as I come here, I clearly have changed the angle to a new angle. So these two deformations are either of elongational or compression-like deformations, or of what we call shear rate deformations, where lengths do not change but angles change. At the same time, you can have pure translation, which means that you are not compressing or elongation. This fluid element just translates on a constant velocity vector. Or you can have pure rotation, which means the angles are not changing. All the relative angles between sides remain the same. The fluid element, just like a rigid body rotation, rotates around an axis. And we saw that to really formulate this and be able to significantly differentiate between all these effects, we need to look at this very useful property which we call gradient of the velocity vector. It's the Nabla or grad operator going through a dyadic product with the velocity vector, which gives us the gradient of the velocity tensor. This is a 3x3 tensor. And if you remember, we were able to break it down to two parts. One part was the symmetric part. So if you remember, when you have a matrix or a tensor, you can break it down into a symmetric part and an anti-symmetric part. And we discussed that these two have different physical meanings and different significant effect on the flow. The first part that sometimes people call, which is the symmetric part, and people call it deformation rate tensor. And people use either E or S. In different books, people use different notations for this part. And the second part, which is the anti-symmetric part of our tensor, is called the rotation rate tensor. And again, depending on book that you choose, people either use R or omega for representation of this part. And as we discussed, this is nothing other than pure rotation of fluid elements. All the other aspects of changing lengths or angles, which are either shear deformations or elongational deformations, are encapsulated inside the symmetric part of this tensor. And this is one of the important concepts that we will use extensively in Module 2. But before talking about that, let's think about what really this part means. So if I look at, for example, E tensor, and write down some of the components of it, I would get things like dvx over dx, dvy over dy, and dvz over dz on the diagonal side. Off diagonal elements, you can calculate them. I just write down one of them for you. You can go back to your notes and see them. But one of them, for example, here will be half of dvx over dy plus dvy over dx. And this is a symmetric tensor, so exactly the same component repeats here. And the idea is the fact that whatever you have on the diagonal section of this tensor gives you the idea of elongational or compressional deformations. Whatever you have on the off-diagonal part, such as these terms, they give you the idea of the rate of change in the angles of fluid elements. The anti-symmetric part will not have any diagonal part. It will have 0 on all the diagonal elements, but the off-diagonal parts are related to the vorticity vector, as we described in your lecture notes and lecture recorded lecture videos that you can check. So this should be a very good review for the main initial topics that we covered in the class. The Eulerian versus Lagrangian description, how we actually connected it to geometrical representation of the flow, which is captured by streamlines, and how we can actually look at fluid elements as they go through these deformations and think about the idea and the fact that the fluid element is indeed deformable. So it may change both its length, for example here, AB to A prime, B prime can change, or it may change its angle, and how we can capture that given the velocity field or kinematics, is captured by this mathematical operator, dyadic product of the grad operator acting on the velocity. The symmetric part and anti-symmetric part of it will give us an idea about deformation rates and rotation rates. In the next video, we continue this review and go to the next set of ideas that were covered in the class.